Hey guys, welcome to another video for chemistry. In this video, I will be discussing covalent bonding. So we discussed before that there were two main types of chemical bonds, and the first one was ionic bonds, and the second is covalent bonding. So you have to recall, as we begin our discussion, you have to recall the main reason why elements create bonds in the first place, and that's to create stability. Recall that elements, as they stand by themselves, do not have, for the most part, except noble gases, right? So if you're kind of mentally picturing the periodic table, the elements on the far right, the farthest right, in group 18, have a full valence shell. They have a full octet. They have all the 8 valence electrons on the outermost shells to keep them stable, right? So they don't typically make bonds because they don't need to. But other elements, on the other hand, other elements lack, they lack either 7 all the way up to or down to 1 electron to gain the full octet. And because of this, because of this shortfall in electrons, they will create bonds. Okay, so because of the incomplete valence shells, they create bonds with other elements. And the first type of bonding we discussed was ionic bonding, right? So ionic bonds are between elements on the very far left and the very far right, between metals and nonmetals. And this particular type of bond, the nonmetals on the right, these elements will practically strip the elements on the left of their electrons to gain a full octet. But coincidentally, the elements on the left, when they have those electrons taken away, they also will create a pseudo noble gas notation. Okay, and that's the main goal. All the electrons, if they're not noble gases, they want to behave like noble gases. They want to be stable like noble gases, and that's done by either taking electrons or giving them away, depending on how many they have. So that's what would happen in ionic bonding. But now with covalent bonding, this particular type of bonding occurs mostly with nonmetals, elements on the far right, and isolating an even smaller group of elements, I want to talk a little bit about a particular type of bonding called, or a bonding that creates a typical type of molecule called a diatomic molecule. Okay, diatomic molecules form covalent bonds. So again, they're on the right side. Now, you'll notice on the far left we have hydrogen there. Hydrogen is also another element that creates a diatomic molecule. Diatomic, just look at the word itself, look at the prefix di, meaning two. So this is a type of bond where two of the same element will create a bond and they will share their electrons evenly. So to better memorize which elements make diatomic molecules, as you look at the periodic table, we'll just kind of imagine a number 7 starting with nitrogen, going to fluorine down to iodine, and then hydrogen 2, of course. So these are the elements that will form your diatomic molecules. And these are types of covalent bonds. So I want to highlight one particular type of diatomic molecule, and that's the one made between hydrogen and hydrogen. So as I look at the two hydrogens, again, they have one valence electron, and they would rather have, so if you recall, the only exception to the octet rule is period number 1, hydrogen and helium. Helium is a noble gas, and it only has 2 valence electrons. So for that first level, if you can manage to get 2 electrons on the s orbital, then you behave the same way as the other elements that have 8. So those are the only exceptions. So helium being the only exception, hydrogen having only 1 electron wants to gain another electron or lose it so that it can have a pseudo noble gas notation also. So so these 2 electrons end up getting shared. So these electrons being shared are what create that handshake between 2 elements. It creates that bond between them. It creates that relationship where each element has something the other one needs, and they share it to to gain full stability. They share those valence electrons. Also, think about the word covalent. It's covalent. They are cooperating. Okay, they are working together. So they are sharing those valence electrons, so they have covalent electrons. So the valence electrons of one element is the same as the valence electrons of the other, covalent. Initially, when you're really dissecting this idea, you have to consider that for example, hydrogen, or any element for that matter, the nucleus of every element is made out of protons and neutrons, and those are and it has an overall charge of positive. And if you recall from previous chapters, like charges in chemistry will repel, whereas opposite charges will attract. So if you think about it, these two elements should not be creating a bond or attracted to each other. They should actually be repelling, because you have two nuclei which have a positive charge should be repelling each other. Likewise, the electrons of each element should also be repelling. So in theory, they should be pushing back against each other, not making bonds. But what's happening is that the electrons from one element are attracted to the nucleus of the other element, and it goes hand in hand with both elements. So the electrons of one element are attracted to the nuclei of the other element, because remember, electrons are negative, nuclei are positive, opposite charges attract. So these attractive forces between the oppositely charged particles in each element, they're strong enough to overcome the repulsion forces of the like charges from each element. And that is what creates that bond, is the fact that the attractive force from each element, the negative electrons of one element are attracted to the positive charge of the nucleus of the other element, and that's strong enough to keep the bonds together. Okay, so now as we kind of go back into our covalent aspect of this, so with the electrons being shared, these two electrons being shared, now each element is satisfied having a full valence shell, creating stability. And we call these electrons that are being shared, we call them a shared pair. Okay, so these are the two electrons that are being shared for each element. Now, there's another way that you can show this principle, and that's by using our Lewis dot structures. So you have the chemical symbols and the two dots representing the electrons that are being shared. And to shorten it up a bit, those two dots you can actually also signify as a line. So anytime that you see a line between two elements, it doesn't mean subtraction, it just means that there's a bond. That is a shared pair of electrons that are creating the bond between two elements. So let's kind of take a bit of a step back real quick and consider another bonding pair. We have helium and fluorine. So keeping in mind that elements want a full octave, right? They want 8 valence electrons to gain stability. Hydrogen has one electron, fluorine has 7. Fluorine desperately wants one more electron, and fluorine just so happens to have that electron. So the bond, one valence from hydrogen, 7 from fluorine, so the bond will be created between those two electrons that are kind of just hanging out, and those two electrons will end up making a bonding pair. Okay, that's that handshake that I was referring to earlier, that cooperation, that covalent bond. So those two electrons are the covalent electrons, right? Covalence. Those are the two electrons that will share. Okay, and then the other electrons in fluorine that are not being shared, those are called lone pairs. Okay, so in this particular bond, you have one bonded pair, one shared pair, and you have 3 lone pairs. Okay, and again, those two electrons that are being shared can be represented by a straight line, and only the ones that are being shared can be represented by a straight line. If they're not being shared, then you just leave them as the dots. Okay, so you have one bonding pair, and then you have 3 lone pairs. Now, staying on this particular bond, hydrogen and fluorine, you know fluorine to be a very electronegative. It's the most electronegative element on the periodic table. So you know it's not going to share electrons very evenly. So the electron from hydrogen will actually spend most of its time in fluorine, signified by that arrow pointing towards fluorine. Okay, and since that fluorine has an extra electron, it will create a negative charge. And that's delta negative that you see on the right. And hydrogen, since it loses that electron, it will create a positive charge, a delta positive. So that's what we call a dipole moment. There's that prefix again, di, meaning 2, pole. So you have 2 poles. So you have different charged poles. You have one positive and one negative. And here we have an electrostatic potential map. And what this type of mapping shows, you'll see this in your textbook and other textbooks periodically, And what this is trying to signify is the unevenness of the electrons and where they spend their time. So if it's red, that signifies that that the electrons that are being shared will spend most of their time with that particular element on the red side. So it's kind of red hot, if you will. And the blue representing the fact that the electron doesn't spend a lot of time on that side. And then you have again your charges that are developed. Now notice on the right side that the oval is thicker on the fluorine side. That's because of the extra electron, the radii size gets larger, whereas the radius of the hydrogen is smaller. Okay. Now, if it's a hydrogen-hydrogen, that dipole moment disappears and it becomes an actually more evenly distributed map where the electrons are actually being shared evenly. And remember, two hydrogens, that's a diatomic molecule, right? And the same thing would happen with nitrogen, oxygen, fluorine, chlorine, and bromine and iodine as well. So here's a bond polarity chart where you can kind of compare. Notice that they're all hydrogens, but then they have the second element, one's fluorine, chlorine, bromine, and iodine. And notice how the electrons, how fluorine, chlorine, bromine, and iodine are much more electronegative than hydrogen. So those electrons will spend more time with the halogens than they will with hydrogen. And fluorine, being the most electronegative, is the most red, so it's going to attract that electron more strongly than any of the other halogens. Okay. Okay, so that's going to do it for our covalent, for our introduction to covalent bonding. I hope this video helped, and stay tuned for other covalent bonding videos as well. Good luck in your study.